computer vision? Okay. Uh, okay. Right.
Yeah, we are on live now.
Great. So for those who are joining like on YouTube, I just wanted to figure out like a little bit more about my audience and just figure out how many of you have some experience with computer vision and or anything related to vision in general. Okay. Basic, none. Okay. Uh, okay. Started to learn recently. Great. So okay. So this way, it's sort of, I think, I guess it makes sense about how I've prepared it. So it'll be very, very informal. I'll be very honest with you. I prepared this, like for past 2, 3 days. So I've tried to make it as informal as possible. So just, just don't shy away from typing whatever you think. If you want to talk, even better, you can just type it in chat. And then I think our moderator, Yash, is also having a look at it while I'm, speaking. Yeah. Uh, So let's just start off. I think this is the sort of idea. First, try to understand why vision. I mean, specifically for robotics. Why is it important for robotics? The principles and basics of image formation. I think this some might know, some might not know. I just thought it'll be nice to figure this out and then maybe learn a little bit more. Like I'm just going to be following the simple pinhole camera model. Yeah, and then a simple homework probably. Your idea, I'll explain to you on how to convert from 3D to 2D and then have all of you guys convert the 2D back into 3D. Talk about image features, both detection and matching. We'll talk a little bit about triangulation and optimization in a robotic framework, and we'll have a quick question and answer. So, I'll be brutally honest. I think some of these things might look very daunting or scary, like triangulation or things like that. But let's take it step by step. Yeah. So I just wanted to make sure that I give you guys like a flavor of what vision for robotics is, and also my goal, at least at the end of this session, is for people to also embrace the fact that vision for robotics is actually the why is it growing now, why is it very important, and at the same time, what are all the things that you might want to have a look at if you want to make a career in this field. Briefly about me. So my name is Diwakar. I'm a data scientist with Geo AI COE. I have about 4 years of work experience and a total of 7 years dabbling with machine learning, deep learning, AI, and things surrounding that. I'm pretty much self-taught. I've taught myself everything I know about this field. And what I do at Geo, I typically play with sensors. So it might be a bit ironic, I think, to some people, So I'm a mechanical engineer. So, and then I went on to do computer vision, which is a bit of computer science. My final year project in my university was in robotics, and I currently play with sensors. So that's more electronics than anything else. Yeah. But I assure you that is exactly what makes me so much excited about talking, in terms of robotics and talking about robotics in general. So if I'm not, doing research on robotics or working on robotics, I'm usually playing chess, gaming, or watching some movies. Yeah. So these are my hobbies. And feel free to reach out to me on, Twitter or LinkedIn. I think it'll be there on chat. So, guys, the first question: why vision for robotics? I want to get an opinion from all of you about why do you think vision is important for robotics, and what can we gain from this? Why do we look at vision for robotics in general? Okay, I think. Okay, starting the process. I think reach the goal, trajectory planning, sensing the visuals, trajectory detection. Advanced vision of ChatGPT that will use vision to become a personal assistant. That's very, very interesting. Next steps in the flow, sensor decisions. Yeah, I mean, so all of these things are right, to make it understand how we perceive the world, like how we perceive, yeah, being aware of its environment. True, very true. So, guys, typically what I'm going to be doing in today's session is a lot of whatever you guys just said in chat. Yeah. So typically when I started writing this, I asked myself this question. I was like, why vision for robotics? Why do I do what I do? What am I impacting or what am I bringing as a change to the world? The first thing that I looked at, I was like, obviously, yeah, vision for robotics. It's clear. I have to do this. This is what the future is. This is where we're heading. But the thing is, vision for robots is very useful. But the question, comes back to how is it useful for us? Giving vision to a robot, how does it impact us, right? Like what change? How are we disrupting the industry, right? It's not just disrupting the industry, but how are we disrupting, what we believe is reality today? So I think the first things, the vision for robotics is sort of forms the basis of everything that is related, not everything, but most of it that is related to AR and VR. So, this is like something new for most people, I think. Even for me, it was surprising because AR, VR basically uses the same principles that a vision for a robot does. Right? The second thing, I think some of you mentioned this in chat as well, was self-driving or autonomous driving or path planning, trajectory planning, navigation, and things like that. Right? So yeah, right. David, I'm actually following chat. So 1D vision systems, 2D vision systems, line scan, area scans, and 3D vision systems, right? So here, basically what happens is in your vision system, when you build a vision system, typically what you're looking at is how we perceive the world, how a robot perceives the world. And the way we perceive the world, like if you're looking at vision, we're looking at it through our eyes, right? So the same when, analogously spoken for by a robot, it basically is using a camera, right? And so typically the job of the camera is to, convert the 3D world to a 2D world, or in essence, basically try to figure out how the 3D world just gets mapped into a 2D world, right? So I basically wanted to say, this is initially was how my presentation was made. Said AR, VR, self-driving, autonomous driving, etc. But typically, right, we always say, etc. does not end. You really typically just want a little bit more. Yeah. So this is something that is, what vision for robotics does. It is very important in cases of mapping and in unexplored environments. It is very important for scene understanding. I think some of you mentioned that in chat as well. And it is also very important in synthetic 2D data generation. So what do I mean by the last point? We'll get to that in a bit. So I just want to talk about very briefly in terms of what mapping is and what scene understanding is before I get to synthetic 2D data generation. So what is mapping? Mapping is basically, maybe I can ask chat, guys, can someone tell me what do you think mapping is? Or what do you think a map is? I'm just turning it over to chat. Okay, something to follow. Percept to action, a structure, representation of something on geography, tool to get location, object identification. So mapping is typically linking two similar objects. Okay. So, okay, probably not in that context, I think. Relation from key to value, right. Location awareness, association of something with its coordinate, and avoiding collision, right? So guys, yeah, all of you have come to the exact same thing that we all say, so if I place you in, say, some environment, a place where you've never been before, and I ask you to, go to a certain place, right? Or navigate to a certain place, You say, I don't know anything. I need a map to go to that place. Right? So typically in a sentence, can I say map is an environment of where you are? Right? That helps you know that, this is where I am in the world. If you're saying this is a 3D map. So map basically is something that gives you relative value to something, like when you say, put it in terms of key and value pair, you have certain keys and you have certain value associated with each of these keys, right? And typically what we look at in robotics as a map is basically the entire world in front of us. What is the 3D map? The world in front of us. And so in order to determine the world in front of us, we sort of need to know where we are, right? And in order to know where we are, we need to have a map of the world. So this is sort of like a chicken and egg problem, right? Like you in order to know where you are, you need a map. And in order to get a map, you need to know where you are, right? So in each of these situations, this is basically the classical problem that we try to solve for robotics, vision for robotics, and this is called the SLAM problem, right? We're not be going deep into that, but a lot of the things that SLAM uses, we will be discussing here today, right? And the second point that I wanted to make about is scene understanding. So this is sort of a derivative of mapping. The better map you have, the more you understand the scene, right? So to the extent where we are able to say that I have mapped this locality, that means I understand this locality end to end. So that basically sort of goes hand in hand. The last part I wanted to talk about was the synthetic 2D data generation. So what do I mean when I say synthetic 2D data generation? So the first point is, if I record a video, say, of me driving about in my colony or, driving about anywhere, right? The way I'm going to be driving about, I am actually taking a 3D world, which is like a real map. I'm converting it into 2D, right? I'm making it into a video. Now, if I am able to regenerate 3D worlds based on this 2D video of mine, right? And then after that, I say that now this is a repository of 3D locations that I have that I can use to record multiple 2D videos. And it will all look hyper real so that you don't even recognize the difference. So how do we do that? That probably is what this course or this introduction is about. So I think for this, I think if we start from the basics, I think this is where we have to start from, like, explain or try to understand how images are formed, right? Basically, we first try to figure out the mapping from 3D world to the 2D world. 3D world being the real world, 2D world being the camera world, right? The virtual world. So image formation from 3D to 2D, that's the idea here. So the way I look at it is object in the world, it's a wonder, how we've created so many great things. The lens, I just call it a magical converter that converts 3D to 2D. Film, that's the proof of magic that it is converted 3D to 2D. Me, I'm sort of a myth breaker. I don't believe in magic. I just believe in logic. Yeah. So I think typically, given the chance, we just want to look at an object that's placed in 3D world that passes through a lens and has a specific focal point and then get captured on a film. Okay. So from here, when we go about, looking at how does this happen, I think this is where it becomes really important for us to understand a little bit of maths. The conversion sort of happens using this formula. And how do we get this formula? Basically, too much math. Let's not, derive it here and now. But there are definitely multiple ways where you can go about online and then figure out how it is derived. So I'm just going to assume this X, Y, Z is actually a point in the world, right? This one, we'll ignore it for now. I'll come back and explain what this is. X, Y, Z are basically 3D coordinates of a point in the world. With respect to what? That also is something that we'll have to define, right? This basically, I'll say, is a 3D point in the world with respect to a certain reference frame. When I say reference frame, I say this is a real world coordinate of a certain point that I've defined to be my origin. And relative to that origin, this is the point in the world. XYZ. So with this XYZ, do you guys think I can represent the entire world? Because math, I can go from minus infinity to infinity and on all three coordinate axes. Yeah. So are you guys following me here? Do you understand the XYZ representation? Yeah. Cool. So as long as you guys are following me, like if any of you guys are not following me, sort of raise your hands or post stuff in the Q&A. I'm following that. I think Yash is also following that. And any point you guys feel that you're not following me, stop me, and I'll try to clarify it here and now. Yeah. So basically, for camera, we have properties of camera that we call parameters of the camera. They may be intrinsic and extrinsic parameters, right? So these camera parameters are basically what convert this XYZ 3D world to UV pixels on an image. And in both cases, what is happening is this entire process basically converts a 3D world into a 2D image. And basically, we can tend to ignore the one here. And this is basically homogenization for those who are, fluent at math. So, okay, so first let me break down this formula on how it works. I think this, if you can like follow a lot of what we're going to talk about later, will make, it won't be that hard. Basically, this is the formula, right, to project a 3D point onto a 2D plane. So 3D point is having a certain extrinsic and a certain intrinsic, multiplying which it converts it into 2D. So what are the extrinsic parameters? Extrinsic parameters that are those that depend on the environment. Like, the camera, R basically stands for rotation and T stands for translation, right? So R, this is basically what you refer to as a rotation matrix. And T is basically a translation matrix. So what do I mean by rotation and translation? So let us assume the camera, for example, the one that's looking at me right now, it's stationary here, right? It's placed here. And I'll assume that my camera, the camera that's looking at me, this one here, is basically, at origin, the global origin. So it has no rotation with respect to itself, and it has no translation with respect to itself. So while I make that condition, can somebody tell me what the extrinsic would look like? Or do you have any idea what it would look like? Yeah, Bobby, I'm just getting towards what extrinsic and intrinsic means. Yeah, nice one, Sagar. I think you get the idea. So typically, I don't want the position of the world is not changing, right? The extrinsic, basically, I said, is representative of the real world. So this matrix, this R11 through R33, this matrix here, the rotation part of it is just going to be an identity, 3x3 identity matrix. And this translation is going to be 0, 0, 0. Yeah. Does this make sense to everybody, or is somebody lost at this part? So, okay. So I'll repeat it once more. See, basically, the extrinsic refers to how the camera moves with time. So let us say you have a certain frame of reference, right? So let us say you have a frame of reference, something like this. Yeah. And with this frame of reference, you have a certain point, right? And with this respect to this frame, this point will have XYZ. Yeah. This is clear to everyone? Now I am saying that this entire line that you see here, is going to be an identity matrix. So what do you think it means with respect to this frame? I think, yeah, Dinesh has raised his hand. Yes, David, that's right. So typically, if I say this is identity, this coordinate system is not changing in any way. Yeah. So what we're trying to look at is that this frame is with respect to this point is exactly here, and this is where my camera is placed. And the translation with respect to this frame of reference, the green frame of reference, is 0. So typically what I am saying is, if the camera is placed according to my definition in the first frame that I'm looking at, the red frame being the camera frame and the green frame being my frame of reference, both of these frames coincide right now. Right? That's how I've defined it. These are the initial extrinsic parameters. Now, when I multiply this with the 3D point, the point does not have to change because my coordinate frame of reference is still the same. And then from there, if you look at this fx, fy, cx, cy, these basically are parameters. Fx and fy are basically referred to as the focal length of the lens. And then cx, cy is basically called the principal point. Yeah. This, I think you can probably read about as definitions of what they mean. But the way when you look at this, right, when you multiply this entire thing, and if you assume that this is identity, right, this basically goes to 1, and these basically go to 0, you basically get a matrix that you get fx into x plus cx into z. Yeah. So the idea basically is, when we get this 3D point on the 2D plane in the initial frame, you're basically saying that camera which is centered here has a camera plane. And when I project this point here, right, the way I'm projecting this point here is controlled by the intrinsic parameter of the camera. So let us say over time, I move the camera a certain direction here, right? And now my coordinate frame sort of becomes like this. And let us say the rotation is a capital R and translation is a small t. Yeah. Now this capital R basically is this entire matrix here. And my small t is basically this vector here. At this point, now you realize, with respect to my frame of reference, the green frame, this green frame, my frame of reference, the camera is moved. So it has a certain new extrinsic parameter that is virtue of the environment here. The environment being how the camera is moved. The point still remains the same. And now when I look at fx, fy, cx, cy, they don't change because the camera is still the same, just that the camera has moved. And now if I consider, I want to project it from here to this frame now. Again, this projection, no, transformation can be in any plane. The rotation basically is giving you rotation about any of the 3 axes. I'm just doing the representation that I'm drawing here is just for understanding. So now that I've moved the camera to a certain extent and the extrinsic has changed, again, the same formula will apply. But this time around, this won't be identity. It will have a certain rotation and translation, which is the extrinsic of the camera. And so, okay, so what does translation mean here? Right. So let's say the camera is axised over this axis, and let's assume that this is like a z axis. Yeah. And now when the frame moves in a certain direction, with respect to this axis, from here to here, there's a distance in the z axis. Yeah. Let us just assume that it moved linearly with respect to z axis. And that I'm referring to as translation, the locomotion of the camera with respect to the original axis in each direction. So now this is my translation of the camera. And let us say the camera is rotated by a certain angle, say 30 degrees or 20 degrees or something like that. So that is my angle of rotation. And that is represented by a matrix called a rotation matrix. I would get into details of how it is derived, but I think that will become much harder than it needs to be. For now, you can just take it in a way that this 3x3 matrix represents rotation of the camera across all three axes. And T1, T2, T3 represents the movement of the camera, that is translation, or the position of the camera. Yeah. And then moving on, the intrinsic basically remains the same. And now you multiply to get the new image. Basically, this is the image at this place. So typically, you can imagine this to be something like you took a picture of a chair from a certain place, you moved the camera, you turned it around, and then you took another picture, right? So this principle of image formation is exactly like this. So is this a better explanation? Are you guys able to understand this now? Great. So typically, this entire definition sort of comes from this. Yeah. So this is basically how the image is formed. And this is like an image that passes through the lens of the principal plane, etc., etc. You can go through principle of image formation. It's not very difficult. Basically, fx is the focal length in the x direction, fy is the focal length in y direction, cxy is the position of the camera, like the center. Yeah. And so basically, when you have an object, it gets passed on through the lens and then becomes an image. It is virtual right now. This is not a real image, right? So are we clear on this? Are all of you parallel with this? Yes, Mike, something like top view. So from here, I think when we move on, like I think I've explained a good part of how images are formed. I want you guys to come up with, how do we get 2D to 3D? I wanted to give this as homework, but probably not, right? So typically the problems that we have with images, right? When we want to get it from an image back to 3D, the first major issue that we go with is we don't have any idea of depth, right? So if you look at this here, it is U, V, and 1. And now we don't have any idea of what the Z component is. The Z is sort of disappeared entirely. Now, how do we get this Z? Typically, the answer is, the way we do that is only by taking two images. Now, let us consider two images and maybe you'll get an idea. So let's take this as an example when we have two views. We have a left view and a right view, right? In cases, you can consider this to be two cameras. Yeah. So one camera is looking at the object X here. The right side camera, the second camera is looking at the object X at a certain, at a different location, typically. So what are you trying to do here? If both of these things are looking at the same object and they're made in a certain way, you are able to create a triangle, yeah? And so from this triangle, the idea basically is now that if you know where the triangle is, you can estimate the depth, which is basically the altitude of the triangle, right? So now if you have two images, you have already solved the problem of, okay, you can't convert from 2D to 3D, but with two 2D images, you can make one 3D point or multiple 3D points, depending on how many points are visible here. Yeah. Is this clear, the idea? Great. So from here, if it were that simple, we probably would have solved the problem in the entirety. It wouldn't be as challenging as it is today. Thing is, if I give you just two images, right? I'll probably show you this. We have to understand what are key points, because we said that take two images, make sure they're seeing the same object. Say this point X. So this is a key point, right? So we just have to figure out what is a key point, and make sure they're observed in two frames. And then we basically have the principle of triangulation, and then we can get depth and convert it into a 3D world. Typically, these are the steps that we need to do. Yeah. So I think it's important for us to understand what these key points are, and let's define them right now so that we understand mathematically and we have a definition for them, down the line, right? So in this sort of image that I have, assuming that, this is like a place, which of these, assume that this circle is supposed to be a key point. Is this a good key point? Okay. What do you think is a good key point here? Okay, that's nice. So for someone who's still a little bit confused, yeah, the corner is a good key point. For those of you who are still a little bit confused, this place is not a key point simply because if I move the green color box a little bit higher up, like, vertically up in this direction, and then basically you wouldn't get to know the difference between any of these places. This place, like a key point here, is no different from the key point there, right? So this is not a good key point. Similarly, if I try to go back here, this is also a very bad key point because horizontal movement is not invariant to horizontal movement. Yeah, top left corner to be more specific. Very right. So this place you basically can make a difference. If it moves in any direction, you know that this key point has moved. You have some semblance of understanding, okay, this is important. And so these kind of points are basically referred to as key points when we work on it. So now we are getting somewhere, right? We started off, in given any two images, we need to first figure out the point X. Now, in both images, we need a point X that is seen, and then we'll be able to make a triangle. Yeah. So in order to do that, we need to detect what are called key points. And now we have a good idea of what would be a good key point. So when it comes to this, what are key points in an image? The key points in an image are distinct to the image. Probably if it moves, it is not ambiguous, and it is as unique to the image as possible. Yeah. So for example, right, like if you have, say, this is the image of the Taj Mahal in India, right? So in this image, there are multiple key points that are there. See, typically if you say a point in the sky, it's a very bad key point because the entire sky is looking the same. You couldn't tell it apart. But points that are on the tower, you might argue that there are points on this tower, the same point might appear on this tower as well, right? And which is actually a very real problem in robotics, right? So in a simple scene also, it will become very difficult to figure out key points. Moreover, after finding these key points, it is very hard to determine if they're key points or not. And then, we just go back to this and then say, now the idea is to find out key points in two images. So, this was like a quick challenge, I just wanted to play this, but right now I don't think in the interest of time, we'll just rush through it. The idea was to spot the difference between the two of these images. So the difference is, sort of this, or the bone, or the flower here, or the plant there, things like that, right? You have multiple differences in the image. That is usually a challenge for us people. Now, we've spotted differences in an image. The next real challenge, for us is to spot the similarities in the image. So in the image, you probably might say that there are about 5-6 differences, right? Right. So there, looking for differences is difficult now. But if I ask you to look for similarities, then you start looking at how many similarities are there in the image. And now I want you to filter out and tell me which of these things could be a key point as well in the image. Right? It's not easy. We probably do it as human beings. We don't find it very difficult. We might have infinite number of key points, right? And then after this, the idea is we have to find out to match these key points as well, right? If I have to match them, what are the principles that I use? You found features of two images, key points of the two images. You describe to yourself how these key points looked, and then decided if they're both similar in the image, they do not have much of a difference, and you're sure that this is the same point in the two images. Now we can basically find the matches between the two images. Now the question is, how do we get the computer to do the same thing? How do you tell the computer that there are two matches present? There are 10 matches present, 100 matches present here. Okay, Lalit, overlapping is a way. OpenCV, okay, using OpenCV, right? But how using what in OpenCV? Brianchi, if I'm pronouncing it right. Biranchi, sorry, my bad. So I think as Biranchi pointed out, right, OpenCV has a multiple set of functions that help you do this. Right, Bobby, correct. So this is for people who are very, very new to this field. So I'm just saying, just check out Swift, Surf, Shitomasi, and all of these things are present on OpenCV. This will give you an idea of how they work. I think one more suggestion is, I think in the blog of Analytics Vidya, there is Ms. Danya who has posted, a bunch of feature detection and feature matchings on basically how to use, these features in OpenCV. I think that's a very nice article that you should have a look at. Yeah. So like I have some examples of this, you guys can have a look at this. So typically, if you consider both of these the same place, right? These are all features and they're matched features in a certain way. So if you look at this, somehow the system is trying to say that this point and this point is matched. So this is basically typically a problem that you will face when you give it to the system. So the question is now, this in itself is a problem, right? If you have very good matches, you are good. So these are some things that the community is still researching and still trying to come up with better ways to do this, right? And in most places, it's doing pretty well, right? So moving across, these are just some examples of matching. Right, Bobby, that's very clear. If the image is rotated or flipped, you still need to be able to find matches if it is necessary. And this actually brings me to a very important question, which is actually the next part of this presentation. What if the image is rotated or flipped? Very important question, Bobby. I just want to bring this up in the very next slide. We talked about the principle of triangulation. If the image is rotated or flipped, how do you propose making a triangle? So typically, if it is something like this, two images are, moving, it's like moving in a certain axis to each other. and then they're looking at the same point. Well, this is pretty straightforward, right? Like you're able to see how to make the triangle. But like you said, if it becomes exactly an opposite, what do you do? Guys, anyone? Okay. So I'm not sure how to pronounce your name. Shakila, is it? Uh, you're saying rotate or flip the second image as well in the opposite direction. Now, if you flip the image, then you have already basically lost your trajectory, right? The first place you knew the camera was here. Second place you knew the camera was here. Between here and here, you know how the camera moved because you have translation and rotation. Now, if you flip the image, you're basically saying that the camera was that side, but I'm just moving it this side for my convenience. The 3D point that you needed to figure out is gone. So that is basically typically one of the biggest problems from conversion. You need to have sufficient parallax along the axis such that you're able to make a triangle. If it is completely in opposite viewing directions, or if it is completely 90 degrees to each other, right? Anything less than 180 degrees, or in any place, it basically has to follow the principle of a triangle. As long as it follows the principle of a triangle, the movement of the camera, we will be able to do something to try and get the 3D point. Sum of any two angles of the triangle should always be greater than the third side of the triangle. That is the principle that we apply here. You can take account of key points and detectors and find the best matches with the help of Swift. And if they can make similar rotation patterns with respect to and flipped, yeah, sure. But then again, how are you making the 3D point there? Your principle of conversion from 2D to 3D was to make a triangle, right? Then therein lies your answer. You have to make a triangle for it to work. So, when 2D becomes 3D, there's another important question here, right? How do you expect to find out what is the rotation and translation of this? I know I just said that so easily, like how you move the triangle and how do you rotate the image is all that matters. How do you propose that we rotate the image, first of all? If I gave you the rotation, it's pretty simple. But if I just give you two images and I gave you the matches between the images, how would you do it? See, Sagar, correct. You can mathematically, shift the camera, but that is not actual movement of the camera, right? You're trying to determine how the camera moved. No, that was my question. How do you figure out the rotation? In this, you see this frame I1, assume that this is image 1, I2 is image 2. Okay, that's a good way. Try to center the point X at all times. But you're saying that with just one point, you will be confident enough to say that both of these have been rotated the right way? But that's a very good method, Igor. The point X is a key point, yeah? It's a key point that you have observed in both images. Difference between the current center and X point. No, so let's put it to you in this way. Let us assume that this point X was actually center of the first image. I move the image in certain way, the camera in certain way that in the second image also it is still in the center of the image. Now in this case, like your definition itself becomes wrong, right? Like both the points X1 and X2 are at the center of the image. right? So, I mean, I understand exactly what you're saying, and this is the only corner case in which it fails. So what I will try to do is I'm not going to take just one of these points. We looked at how many features are getting matched here, right? And a lot of them are doing a very good job. So why should I just take one point, match it, and then triangulate only that one point? I'll take a bunch of points here. And these bunch of points, basically, if you look at this, all of them are inclined at a certain way, right? Now, what I want to do is in mathematics, this basically comes into picture where we call this system as epipolar geometry, right? So what happens is C1 is the center of the first camera. C2 is the focal point of the second camera, or the second point, it's the center of the second camera. You're passing a ray through X1 and you assume that it is at some point X. Similarly, you have a ray passing through X2 and that meets at the same point X because you've determined X1 and X2 are the same point X, right? And now that this has happened, you've basically found a match in the image that basically is making a line or rotating it in a certain way. Now, my point is I want to make sure I'll keep one image straight, constant. That is defined as identity or my first image. And the second image, I'm basically going to rotate and move it in certain ways such that both of these things lie on a straight line. And this straight line is basically referred to as epipolar line, right? So what happens here is now you are basically rotating the image in such a way that you get a line between the two centers. The two centers basically stand on a straight line. And the image that is rotated, by how much it is rotated or moved in order for you to get the same point intersect. That is basically referred to as, this basically C1, E1, E2, C2. This line is referred to as epipolar line. And the plane P in which they intersect is referred to as the epipolar plane. You can read up more about this mathematically. I don't want to get into too much maths. So this way, what is happening is you are confirming that this bottom line is going to be horizontal. I have rotated the image in such a way that this bottom line is horizontal. How we do that? Yes, P is a hyperplane. So in this way, what happens? You basically set up an entire system that is revolving around this with keeping I1 as your fixed constant part, identity. I2 is with respect to I1, so it has some rotation. Yes, David, it is stereo. So with two views, basically what happens is you have this point X, and with this point X, you are somehow able to generate the 3D world, yeah? So typically, yeah, this is what we did. The question is now, can we get the 3D point? Are you sure that this is the 3D point? That's what we discussed, right? Now we know rotation between the two images. We have made a straight line between the two images, a straight line. Then we interpolate to make a triangle, and voila, we have the depth. But the issue here is we still don't know the distance between the two images. We get the translation, but how do you know that the translation is right? So basically, the issue that comes along with this is we have no idea of the scale between the two images. Can be any amount of scale. And so the image might become smaller or larger. Any ideas on how we can fix this issue now? If you guys have some suggestions, we can take them, or else I'll tell you the way we've done it historically. So guys, typically what happens is in the last bit here, to fix this, what we try to do is we follow the same principle that we did till now. but not just for 2 images. Let's take, say, n images. And if we are able to track the same point X across n images, this point X across n images, then we have n images in which the same point is observed, and we make sure that we optimize the rotation and translation for all of them together in order to get your rotation and translation, and then keep fixing it. It's an iterative process. It will continuously fix itself. And that typically where your optimization comes into play. Yes, you have to take planes identical. Yes, you have to create multiple planes now. You have to make multiple epipolar planes. So when we look at optimization in this process, right, we say, do we really need it? What is that to optimize? Basically, every time you do an estimate of the rotation translation, the question answers itself that it's an estimate of rotation and translation. It's not an accurate rotation and translation. What can be optimized? Both. See, now what can be optimized typically is, yes, Bobby, that's exactly what we'll be doing. We'll continuously be rotating all the images except the first image. Why? Because we've already determined that the first image is fixed at identity. If you don't fix at least one image, what is going to happen is every image is free to rotate in every which way. You don't have any constraint to the system, so you have infinite number of solutions. Exactly, so that you can track the changes across the images. Right? So now we go on to what can be optimized. We can optimize all the poses of the camera. Basically, pose of the camera refers to rotation and translation. And now each time the rotation and translation of the camera changes, the same time the point X also moves in the world, right? Because you made the point X in the world based on what your estimation of rotation and translation is. If the rotation and translation of X is changing, the point X in the world is also changing. And so if the point X in the world is changing, the rotation and translation in your camera also should change. So this is basically the part where I said the chicken and egg problem. If one changes, the other changes with it. And the only thing that we have that ties all of this down is the fact that we know, thanks to deep learning, that the point you've observed in both the images are the same point. And that is the only constraint that you actually legitimately have. Everything else is an assumption. And so further, when we go on, now that we know what can be optimized, $1 million question is how to optimize it. How many ways can you optimize it? This is very interesting, by the way. When you figure out that there are so many things that can go wrong, will go wrong, and nothing, you're in control of nothing in the world, yet you have to optimize it for something better. What do you optimize? You've already figured that also out. Now you're figuring out on how to optimize it. I think this is where it basically comes down to the wire. The way what you optimize, the error in detection, error in matching, error in extrinsic determination, the rotation and translation, the error in triangulation, because you have to find out what X is, the depth is changing again, and error in tracking, because if I'm giving you n different frames, tracking it across those n frames is not easy. Everything is a problem here. So now all of these errors needs to be managed, and you have no constraints to the system. The only constraint is you've observed the same point in 2 images or n images, or you think you have observed. If you look at how uncertain I am in saying anything, you should realize that everything is uncertain here. And that is precisely why this is very interesting. So the way we optimize it, or how we handle all of these errors, the process that we refer to is called bundle adjustment. So typically, guys, this is like a pun that I make. Like I think the chat by now has seen what my Instagram handle is or my Twitter handle is. It's basically bundle adjuster. In a world where everything is uncertain, be a bundle adjuster, right? So what is bundle adjustment or BA? So basically what happens is the idea of bundle adjustment comes from the fact that I have created a 2D world where I am very certain about my matches, thanks to deep learning. And based on these matches, I've determined a 3D world. but I still always know my camera intrinsic matrix. So you have to keep adjusting, making small changes every day, every minute, every camera frame, and every 3D point. Make micro adjustments in such a way that you get the accurate rotation and translation between the two frames. And when you get an accurate rotation and translation, the world outside also changes. And you get a very accurate view of the world. Accurate by the standards of how accurate you have your rotation and translation, right? And how do you fix this? Basically, you minimize something called the reprojection error. So what is a reprojection error, right? So here, if you remember, why did I stop slowly and talk to you about the image formation or the point of camera, right? Why did I stop here for extrinsic parameters specifically? So you assume a set of extrinsic parameters, you assume an XYZ in the world, you know FX, FY, CX, CY, because the camera parameters, you can calibrate it very accurately. And basically, you multiply all of these three things together, and then you get a UV, right? You get a point. And this is basically a point in the image. What I try to do is, based on this XYZ in the world, I try to get a point in the image. Then I look at the point on the actual point on the image, because that I have. And then I say that, based on all of this, if I have gotten UV and I have a U cap, V cap, the actual UV is given in the image. U cap, V cap is some point that is, say something like, if this is the image, my projected point is somewhere here. The actual point is somewhere here. So there is an error between these two, right? This error, if I minimize, the way I minimize it is by tweaking these values. And the same tweaking I'm going to do for n different frames and minimize the error as much as I can. Then I am going to get a very accurate RNT and very accurate XYZ. And that basically makes it all the more interesting that you optimize all of these things together as a bundle. And that is why it is referred to as bundle adjustment as well. So how are we minimizing using in-bundle adjustment? There are multiple ways of it. These are three suggested readings that I'd want to give it to all of you guys. Cauchy's gradient descent is also called as steepest gradient descent. I think anybody who's done anything with computer vision or any sort of learning algorithm by now should basically be at the point where you refer to as steep gradient descent, which is the gradient descent that you use, vanilla gradient descent, right? That's the more commonly, here that is called Cauchy's gradient descent. At the same time, we have Gauss-Newton optimization, which basically says, if you want to figure out if it's a maxima or minima, and then based on that optimize further, Gauss-Newton lets you do that. And Levenberg-Marquardt is basically a combination of both of these gradient descents that takes in both of their inputs and outputs, and that comes back with a better optimization method. So you guys can have a look at all of these three. If you go incrementally on each of these things, you first understand what steep gradient descent is. You then understand what Gauss-Newton is. And then Levenberg-Marquardt is sort of putting both of these together, typically. So apart from this, I just wanted to leave you guys with some research areas in the field. And, if you're really interested to pursuing this further, some research targets that are happening is, this is like an annual challenge that's posted every year. This is called the image matching challenge, where individually people are trying to get better key points, match these key points in a better way and get better matches out of them. The second one is obviously the optimization methods, because we've just seen it's an infinite optimization problem. You can pick up any small part of it and make it better. And the third part, basically, if you can do both of these very well together, the final output is 3D reconstruction, which needs to be optimized further. Well, that's pretty much it for me, guys. I'm not sure if it was boring, interesting, or I took way too long. So I'm happy to take any questions that you guys have, that the Q&A. I have a camera, and what can I can do to get the scene in front? and make some predictions. Uh, I think typically, I think this is where uh, deep learning has done a lot of things, right? Object detection, object classification, and all of these things. How can you build a basic robotics prototype? Uh, Mayank, you have to first figure out what is your prototype for, right? So typically, uh, a basic robotics prototype, anything can be a prototype. Previous slide, okay. This one, Bobby. Yeah, David, you can go have a look at Ross. Uh, as a person with beginner level understanding in computer vision, how can I switch to the 3D world? Uh, well, typically, there are a few things that you have to sort of understand when you're coming to the 3D world, right? Like, because there are multiple ways to look at 3D world. So I just described the most, basic version of it using just camera. So typically what we try to do, my work is also related to this, is we have multiple sensors in the world, right? You have a lidar sensor that can actually give you depth straight away. You have an IMU that can help you determine the rotations and translations very accurately. So each of these things can combine to come and work together to give you a very good output. So each of these things would work in their own way to come out, and each of them have their own uncertainty. So this uncertainty is what we have to map and look at how we manage this uncertainty. I think it's a game of probabilities and optimization. So yeah, I think there are a lot of ways you can enter the 3D world pretty much, but you have to figure out what is the niche you want to fill. Okay, Lalit, I'm not sure why LinkedIn is throwing that error, but thank you for the follow. Guys, you can feel free to just tag me on any query or questions or anything of that sort on Twitter. I'll be happy to respond there as well. And some YouTube video suggestions that I might have for anyone who wants to get into this. There is a video, I think, a video live stream of where somebody builds exactly what I've said. It's called Twitch Slam. You can basically have a look and understand this better. Like each and every part of why what is done will basically be shown. And yeah, I think that's a good place to start if you guys want to do it. And the second thing is, yeah, some research areas is basically you can have a look at the image matching challenge and some recent papers from CVPR. So I think 2022, I think the best paper award went to an optimization method that they described. I think the title was Learning to Solve Hard Minimals. This was sort of the What is a Planck unit? Sorry, David, I have no idea, honestly. Uh, I'm not sure, Bobby. I think it was George Holtz. He also provides the code, and yeah. Uh, yeah, I'm free to take any questions, or if anything else, we can sort of stop here.
Thanks a lot, Diwakar.
Yes.
On behalf of Analytics Vidya, I would like to thank you for your time and delivering such a wonderful session. I am sure our audience found it insightful and hopefully we can conduct more such sessions with you. Guys, you can find the LinkedIn and Twitter of the speaker in the chat. I hope you guys have filled in the feedback poll. If not, I request you to please fill in the poll about feedback as it helps us to conduct such more sessions. If you wish to conduct a webinar or facing difficulty in registering, connect with us at data@analyticsvidya.com. The recording of the session will be available within 2 days on our YouTube channel, whose link is in the chat section. We will be back with another session of data tomorrow. The link is in chat section. Till then, bye bye and keep learning.